Right. So the question is asking for the concentration of the hydroxide ions in a solution on completion of the reaction. Right. Because we're talking about the completion, we have to know between the two which one is the limiting reagent and which one is the excess reagent or the reagent in excess. Okay, so we have to know which one is going to react completely. Because we're talking about completion of the reaction, we have to know which one is going to react completely and which one is going to be in excess, meaning which one is going to remain after the reaction has completed. So after the reaction is completed, one of the two, either the acid or the base, is going to remain in the solution. And that is also going to determine the pH of the solution. However, we're going to get that in the next question. So because we're talking about the completion, we have to know which one is the limiting reagent, which is the one that is going to react completely, and which one is going to be the reagent in excess. That means the one that is going to remain after the completion of the reaction. Right. I don't know. When I explain chemistry, I don't know if I become aggressive or I become emotional, but I find this to be so satisfying and so like simple that I get emotional when learners do not understand it, because it makes sense. Maybe it is because I've been in a lab, like a physical lab before, so I understand how these things happen. I have done a titration. When I say titration, I mean like a physical titration. I have done titration personally, so I understand everything that I'm saying here. So I get so emotional when learners say that they don't understand what is happening. They can't even, so that is why maybe I become aggressive when I be explaining this chemistry concepts. But I hope that is still on the same page and you are understanding. If not, please let me know so that I can try maybe to explain in a different way. Okay, so I hope that we're still on the same page. Let us continue. So we have to make sure that we identify the limiting reagent and the reagent in excess. Right, so how do we do that? We're going to determine the number of moles of the base and the number of moles of the acid and then compare them. So let us start with the base. Right, so the number of moles of the base. Okay, well, let me actually mention something that I know that you might actually need it. Okay, so there's so many different ways in which we can determine the number of moles of any substance. So there's 4 formulas that we're going to utilize in the whole of chemistry, meaning from question 1 to question 10 or even 11 if there's a question 11. Okay, from question 1, meaning the whole question paper. There is so many different ways in which you're going to determine the number of moles. You can be asked for the number of moles in the multiple choice question, in the question 1, and in question 2, question 3, question 4, question 5, all the way to question 10. They may ask you for the number of moles. So that means stoichiometry is very, very important. Quantitative aspects of chemical change are very, very important in chemistry. That is something that we learn in grade 10 and grade 11. So you have to apply that in grade 12 as well. So stoichiometry is very, very important in grade 12. So you're going to be asked to apply stoichiometry in any question at all, especially acids and bases. So we have to remember how to apply the stoichiometry. That means you have to have a very high level of skills of stoichiometry to be able to pass chemistry in grade 12, okay? So there's so many different ways in which we can determine the number of moles. So what are those ways? We have 4 different formulas. So we can determine the number of moles by saying it is equal to the mass over the molar mass. That is the first formula. We can also say the number of moles is equal to concentration multiplied by the volume. Okay, we can also say the number of moles is equal to the volume of a substance divided by the molar gas volume of that same substance. We can also say the number of moles is equal to the number of particles of a substance divided by the number of particles per mole of that substance. So we have 1, 2, 3, 4 different formulas in which we can calculate the number of moles of any substance, and also the bonus equation, which is the number of moles of an acid is equal to concentration of an acid multiplied by the volume of an acid, and divided by the number of moles of the base is equal to that divided by Cb multiplied by Vb, which is the volume of the base, right? So we also have this bonus equation which we can utilize to calculate the number of moles of either the acid or the base. Okay, so that means we have 5 different formulas in which we can use to calculate for the number of moles. Depending on the context and the information that we have, you're going to select the relevant equation here. For example, in this example that we have here, we have been given the concentration and the volume. The fact that we've been given the concentration and the volume, we have to identify the equation that we have to utilize to calculate the number of moles in this context or in this example. So the fact that we have the concentration and the volume, we have to look at our 5 options and be like, which one is going to be relevant here? So is it going to be the mass and the molar mass? No, because we have not been provided with the mass. So that means we have 2 unknowns. We have the number of moles and the mass unknown. So that means we can not determine the number of moles, because we cannot determine for 1 unknown for 2 unknowns in using 1 equation. For us to be able to determine for two unknowns, we have to have two equations, meaning we're going to do the simultaneous. So that means we cannot actually utilize equation number 1. What about equation number 2? Equation number 2 is perfect because we do have the concentration and the volume. That means we can determine the number of moles, right? What about equation number 3? For equation number 3, we do have the volume. We also do have the volume at STP, right? So that means we can actually technically utilize the equation 3. However, the reason it is not relevant in this question, it is because we do not know the conditions of this equation or of this reaction. They have not told us that this reaction is taking place at STP, which is the standard temperature and pressure, which standard temperature is 0 degrees and the standard pressure is 101.3 kilopascals, right? So because we do not know the conditions of this reaction, we cannot assume that it is at STP. Okay, so the fact that we do not know that it is STP, we mustn't assume that it is STP. That is why the molar gas volume is relevant, and we do not know what it is in this specific question. So that means now we have two unknowns. That is why we cannot actually utilize equation number 3. What about equation number 4? We do not have the number of particles of either of these reactants. So that means equation number 4 is also irrelevant. What about equation number 5? Equation number 5 is perfect because we want the number of moles. We do have the concentration of the acid. We do have the number of moles of, we do have the volume of the acid. We have the concentration of the base. We have the volume of the base, and we can determine both the number of moles of the acid and the base. That means equation 5 is perfect. That means we only have two options, this one or this one. Okay, so that is how we identify the relevant equation to utilize in a specific acid and base question. Okay, so let us eliminate the ones that are not relevant and keep the ones that are relevant in mind, right? So between the two, which one is going to be convenient for us to utilize, or the simpler one? It is going to be equation number 2. Why? Because it is shorter, and we're going to calculate number of moles of an acid and a base respectively, meaning separately. We're not gonna calculate them at the same time. By the way, this is only one equation, and it has two unknowns. We do not know the number of moles of the acid. We also don't know the number of moles of the base. So that means we cannot determine both of them using one equation. These are two unknowns. We need two equations at least. You know what I'm saying? So that is why this is also irrelevant. So that means the only convenient one is equation number 2. So I hope that we're still on the same page. Right. So let us erase everything and then keep in mind that we have to utilize equation number 2. If you have any questions, please let me know in the comment section. Maybe there's something that you do not understand. I can actually make a special video specifically for you. Okay. Right. So let us determine the number of moles of the base. So of the base phase. So number of moles of this base is equal to concentration of the base multiplied by the volume of the base. So it is going to be equal to what? It is going to be equal to, concentration of the base is 0.25 moles per cubic decimeters. If this was in moles per cubic centimeters, we had to convert from centimeters to decimeters. So fortunately enough, it is already in cubic decimeters. So that means we are on the safe side. So 0.25 multiplied by the volume, which is 0.8. We're going to press that into a calculator and be like, the number of moles of the base is 0.25. So pressing a calculator, we have 0.25 multiplied by 0.8, and it gives us 0.2. So that means the number of moles of the base is 0.2 moles. So we have to keep this in mind. So let me write down that information. So the number of moles of the base is 0.2 moles. So we have 0.2 moles here. 0.2 moles. What about the number of moles of the acid? Number of moles of the acid is equal to concentration of the acid multiplied by the volume of the acid. So we're going to substitute, like, concentration of the acid is 0.1. So 0.1 molars multiplied by the volume of the acid, which is 0.5. So we're going to press that into the calculator and determine the number of moles of the acid. So 0.1 multiplied by 0.5. Yeah, 0.5. What is that equal to? That is equal to 0.05 moles, right? So we have 0.05 moles, right? So that means we have the number of moles of the acid as 0.05 moles. So we have 0.05 moles. So how do we determine the limiting reagent and the reagent in excess here? We're going to be like, okay, so according to this balanced equation, every 1 mole, so the ratio is 1:1, right? So for every 1 mole of the base, we're going to have 1 mole of the acid. right? So we have 1:1. So we have base here, we have the acid there. So there's 1:1 ratio, right? So for every 1 mole of the base, we have 1 mole of the acid. What about when we have 0.2 moles of the acid? How many number of moles are we supposed to get for the acid? Because this is 1:1, we must also get 0.02. We must also get 0.02 moles of an acid. So we're going to compare this number of moles that are available with the number of moles that are required. So this is the number of moles that are available for the acid, and this is the number of moles that are required for the acid. Okay, so this is available versus required, right? So we're going to compare them. We only have 0.05 moles available, but 0.02 is, actually 0.2, not 0.2. What the? Okay, so we have 0.2 moles that is required. We only have 0.05 moles available, but 0.02 is required. For example, you want to attend maybe a certain concert, right? So you only have 100 rand in your bank account, or you only have 100 rand cash, right? But what is required for you to enter into that concert is 200 rand. So are you going to be able to enter into the concert or not? You are not going to be able to enter into the concert because you do not have enough. Whatever that you have available is less than what is required. That means they want 200 rand. They want 200 rand. You only have 100 rand. So that means the number of moles of the acid available is less than the number of the moles that is required to balance what? To balance the base, or to neutralize the base. Remember that it is the acid that is neutralizing the base, right? But we only have this 0.05 moles available, and 0.2 is required. That means we have only a limited. We're not going to be able to neutralize the base completely. So what is the one that is in excess and which one is the limiting? That means the limiting reagent is going to be the one that is going to react completely, which is the acid in this example. When the available is greater than the required, that is an information that you're going to need, and you're going to need to write this into your notes. So when the number of moles available, this also applies to mass, by the way. When the number of moles or the mass available, when the number of moles of the mass available is less than the number of moles required, the number of moles required, or the mass required, then that is the limiting reagent. Okay, so that is the limiting reagent. Please take this information and add it into your notes. I'm going to erase it, remember that, okay? So please pause the video and then write this into your notes. So when the number of moles or the mass available that we have available is less than what is required, then whatever the substance is the limiting reagent, right? And then when the number of moles available, I don't want this video to be too long, so I'm just going to write the abbreviations. So when the number of moles available is greater than the number of moles required, or the mass available is greater than the mass required, then that is that reagent is in excess. That reagent is in excess. Okay, so you're also going to need this information. Please add this into your notes. Okay, so this is a G, by the way. I'm so sorry about that. So the reagent is in excess if its number of moles of the mass available is greater than what is required. So I'm going to erase this. Hopefully you have actually added it into your notes. Right. So that means, utilizing this principle, we now know that the acid is the limiting reagent and the base is the one that is in excess. That means the base is not enough. The acid is not enough to completely neutralize the base. So the acid is not enough to completely neutralize the base. Right. So that means the limiting reagent. So the limiting is equal to the hydrochloric acid, and the excess, the one that is in excess, is equal to what? To the base, which is the sodium hydrogen carbonate. Right. Now that we are here, we can actually calculate the concentration of the hydroxide ions in the solution on completion of the reaction. How are we going to do that? Okay, so we're going to be like, how many number of moles are going to react of the acid? So we know that the number of moles of the acid that are going to react are 0.05 moles. So that means the number of moles of the acid is 0.05 moles. Right. So that means the number of moles of what? The number of moles of the base that are going to be neutralized the number of moles of the base that are going to be neutralized, since the ratio is 1:1, is going to be the same. So the number of moles is also going to be 0.05 moles. So that means 0.05 moles of the base is the one that is going to be reacting. Okay, so this is the one that is going to be reacting, or the one that is going to be neutralized. So we're going to only neutralize 0.05 moles of what? Of the base. So what is the number of moles of the base that is going to remain? The number of moles of the base that is going to remain, okay, let me say remain in brackets. So the number of moles of the base that is going to remain is equal to the number of moles total. So the number of moles total minus the number of moles reacted. So the number of moles that are going to remain, remember that we said that the base, the acid is going to neutralize the base. But since the base is in excess, that means only a certain amount of a base is going to be neutralized, and some is going to remain after neutralization or after the completion of the reaction. So that means base is going to be in excess and is going to remain. So what is the number of moles that is going to remain? The number of moles that is going to remain is going to be the total minus what is going to be reacted or what is going to be neutralized. Okay, so what is the total number of moles of the base? It is this, which is 0.02. So we have 0.2 moles available, which is the total number of moles of the base, minus the one that is going to react, which is what? Which is 0.05. So we have 0.05 moles. So what is the number of moles of the base that are going to remain? So the number of moles of the base that are going to remain after completion of the reaction is going to be 0.2 minus 0.05. So we're going to press a calculator and we're going to be like 0.2 minus 0.05. And what is that equal to? That is equal to 0.15. So that means the number of moles of the base that is going to remain is 0.15 moles. Okay, so that's the information that I'm going to need to write at the top there. So I'm going to erase this. So I hope that you're going to be able to keep this in mind and also in your notes if you're actually following this video so far. Okay, so I'm going to need to pause the video and then write this information that I've done here, because you're going to need a step-by-step on how to answer this question. Remember that, right? So I'm giving you the step-by-step on how to answer this question. So if you're following, please write this information into your notes. All right, so I'm going to erase this. So please pause and then write the information. Right. So now I have actually calculated the number of moles that is going to remain in the in the whatever what is it called, maybe in the conical flask. So the number of moles of the base that is going to remain or in excess or excess, the one that is excess is going to be equal to 0.15 moles. Right, so the same as calculate the concentration of the hydroxide ions in the solution on complete of the reaction. Right, since the acid is going to neutralize the base, the number of moles that have already been neutralized by the base, we are not going to consider them because they've already been neutralized. So we're only going to have a certain number of moles that have not yet been that have not been neutralized. So we're only going to consider the number of moles that are going to remain. That means 0.05 moles of the base are already neutralized. So that means the number of moles that are going to remain is the one that we're going to consider here. So the number of moles of the base that are going to remain are the ones that are going to give us the what? The hydroxide ions. So since the acid has already neutralized the base, we no longer have the acid because the acid has completely reacted with the base. We only have the base remaining in the reaction mixture, which is the conical flask. So we only now have the base remaining in the reaction mixture, right? So what is going to be the concentration of the hydroxide ions? Okay, so we're going to calculate the concentration of the hydroxide ions in the following way. We're going to be like, since it's only the sodium hydrogen carbonate that is remaining, so it's going to react with water, of course, to give us what? To give us the hydroxide ions. Okay, so how is it going to give us the hydroxide ions? So we have the base and then we have the water that are going to react to give us the hydroxide ions, right? So since this is the base and this is the acid, remember that according to what? According to LB theory or Lorenz-Bronsted theory, this is the base and it has to do what? It has to accept a proton. So that means the acid, which is the water, has to donate the proton. So we're going to have what? We're going to have sodium hydrogen. Actually, it's going to be H2, right? So it's going to be Na2CO3 plus really plus? Yeah, it's going to be that plus. And then we're going to have plus OH minus. Okay, so let me show you write this formally and also neatly for you to be able to see it. So I hope that you understand that it's going to be the base and water reacting, and the water is going to react as an acid. So we're going to have NaHCO3 remaining in the conical flask or in the reaction mixture, and it's going to react with water because this is a solution. Okay, so this is going to be the solvent, and then it's going to give us what? Because this is going to be the base 1, and this is going to be acid 2. So this is going to donate a proton H plus. So that means this is going to receive a proton. So we're going to have a plus here. So we're going to have NaH2CO3 plus. Why is it plus? Because it has received a proton. Then of course, after this water has lost a proton, is only OH minus is going to remain. That means it's going to lose 1 hydrogen. So we're only going to have OH. 1 oxygen and 1 hydroxide. 1 oxygen and 1 hydrogen. Okay, so that is what is going to happen here. We're going to have acid. We're going to have acid what? Acid 1 here and base 2. So we're going to have base 2. See what has happened here. What has happened is the following. So after this base 1 has accepted a proton, it is going to give us acid 1 here. Right, but what is going to happen on the product side? What is going to happen is that the concentration of the hydroxide ion is going to increase. So the concentration of the hydroxide ion is going to increase. So look at this. So we have the concentration of the hydroxide ion increasing because we have plus OH minus. I hope that we're still on the same page and everything's still making sense. Okay, so please allow me to continue. All right. So the ratio of all of this is 1:1. Okay, so we have sodium hydrogen carbonate reacting with water to give us sodium hydrogen carbonate ion plus the hydroxide ion. Right, so look at the ratio. The ratio of the base here is 1:1. So the ratio of the base is to hydroxide ion is 1:1. So we have NaHCO3 is to OH minus. So the ratio is 1:1. So that means the number of moles of the base that are remaining is going to be the same as the number of moles of the OH minus. So since we know that the number of moles of the base remaining is what? Is 0.05 moles, 0.15 moles. That means the number of moles of the OH is going to be, or hydroxide ion is going to be also 0.15 moles. Because the ratio is 1:1. What we're interested in is this. So since now we have the number of moles of OH minus or the hydroxide ions, we can calculate the concentration by saying concentration. This is the formula that we have at the back of the paper or in the formula sheet. So concentration is equal to the number of moles divided by the volume. The number of moles divided by the volume. So how are we going to calculate the concentration of these hydroxide ions? So we're going to calculate the concentration by saying its number of moles is 0.15 moles, right? So we have 0.15 moles divided by. So what formula are we going to utilize in this example or in this calculation? We are going to utilize the total volume. Okay. So I don't know if you want me to show you how we're going to calculate total volume, or I don't know if you're going to understand this in the following way. Okay. All right. So this is going to be. Please look at this, okay? This is coffee, by the way. I didn't actually finish my coffee. So this is coffee, okay? So please consider this. Consider this what? Consider this the base, okay? So this is the base. So I'm going to add the acid. Please wait a second. So I'm just gonna be back right now. I'm just gonna collect some water, okay? So I'm gonna pause the video and I'm gonna continue. All right, now I'm back. So this is me neutralizing the base. Remember that I said this coffee of mine is the base, right? So I have the acid with me, by the way, it's water, but I'm just trying to make sure that you understand the scenario that we have here, okay? So we have the base inside this conical flask. We're just going to assume this is the conical flask. So I'm going to add the acid to neutralize it. Of course, we have the acid as the limiting reagent, so we don't have enough acid to balance this, right? So we're going to add the acid. So this is us adding the acid. We're adding the acid, 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 and then we ran out of the acid. Okay, we ran out of the acid. Now that we have ran out of the acid, the base has been what? The base has been neutralized, but it has not been neutralized completely. There's still some base remaining. So the amount of the base that is remaining is 0.15 moles. right? So the base that is remaining inside of this conical flask is 0.15 moles, right? So this 0.15 moles, it has given us 0.15 moles of the hydroxide ions because the ratio is 1:1. Now that we have 0.15 moles of the hydroxide ion, what is going to be the volume that we're going to utilize? Remember that the volume is going to be the total volume, because what is going to be the total volume in what is going to be the volume that these hydroxide ions are flowing in. So these hydroxide ions are floating or flowing inside the total volume, not just the volume of the base. So we're not going to utilize the volume of the base, which is 0.8 cubic decimeters. We're going to utilize the total volume, which is the volume of the base and also the volume of the acid combined. Okay, so that is why we're going to utilize the total volume. So I hope that we are clear with that. Okay, so here we're going to utilize the total volume, which is going to be the volume of the base, which is 0.8, plus the volume of the acid, which is 0.5 cubic decimeters. So that means we're going to be like 0.8 plus 0.5. What is that equal to? That is equal to 1.3. So we have 1.3 cubic decimeters. So we're going to write 1.3 cubic. Where's my pen at? Where did I put my pen at? Oh my God, where the hell I put my pen at? Have I lost my pen? Give me a second, I'll be back. Okay, yeah. Okay. Okay, I got a pen now. So the volume is 1.3 cubic decimeters as we have utilized the calculator. That means the concentration of the hydroxide ion is going to be equal to 0.15 moles divided by 1.3 cubic decimeters. So we have 0.15 moles divided by 1.3 cubic decimeters, and that is equal to two decimal places we have 0.12 molars. So that means the concentration is 0.12 molars, or if you're not used to molars, you can say moles per cubic decimeters. So that means the answer is 0.12 moles per cubic decimeters, and that is how you get your 8 marks. Okay, so yeah, that is how we answer this question. So I wanted to make sure that you understand it. So I'm going to show you a picture on how to do a step by step. This was just me explaining this. Okay, so I'm gonna show you a picture showing how to do every step neatly. Okay, so yeah, that's what I'm gonna do. All right, now let us go to 7.2. Okay, so we are on the next page because I read out of space from the previous page, right? So what I meant is 7.2.2, not just 7.2, okay? So that was 7.2.1. So 7.2.2 says to us, calculate the pH of the solution on completion of the reaction. Okay, so I have to make sure that I keep the information that I had initially calculated in mind for me to be able to determine the pH of the solution after the completion of the reaction. So I know that I had the number of moles of what? Of OH as 0.15 moles, right? So I had also calculated the concentration of the OH minus to be equal to 0.12 moles per cubic decimeters. So we need the pH. How do we calculate pH? pH is calculated by saying pH is equal to negative logarithm of hydronium ion concentration. Right? So what we need is the concentration of the hydronium ion. How are we going to determine the concentration of the hydronium ion? We're going to utilize the concentration of the hydroxide ion to determine the concentration of the hydronium ion. So how are we going to do that? We're going to be like, well, when water reacts with water, I don't remember what this principle is called. I think it's called what is this principle called? I actually forgot what this principle called, but it has to do with the Kw, which is the constant of water. So when water reacts with water, it is going to give us hydroxide ion plus hydronium ion. So one water is going to be an acid 1, giving us base 1, and this one is going to be base 2, giving us acid 2. Right, so that is going to be the conjugate base pairs for when water reacts with water. Right, so you can see that the ratio of the hydronium ions, hydroxide ions to hydronium ions is 1:1. Right, so according to that principle that I had just forgotten, I know that Kw is equal to the concentration of the hydroxide ion multiplied by the concentration of the hydronium ion. So we need the concentration of the hydronium ion, and we know that Kw is a constant, and it is equal to 1 multiplied by 10 to the power negative 14. I think you have this at the back of the paper or uniform notation. Let me just confirm that. So Kw, I think Kw is a constant. It's fine. This is something that you're supposed to know by heart. So this is something that you should know by heart. So it's 1 multiplied by 10 to the power negative 4. It's a constant. It never changes. So what is the concentration of the hydroxide ion? This is the concentration of the hydroxide ion. It is 0.12 moles per cubic decimeters. Okay. So we have 0.12 molars. So I'm just gonna write 0.12, and then the concentration of the hydronium ions. So we're going to divide both sides by 0.12. Therefore, the concentration of the hydronium ions is going to be equal to, then we're going to just press our calculator right there. So we're going to be like 1 times 10 to the power negative 14 divided by the answer. What was the answer there? Oh my god, actually, okay, let me just say 0.15 because I don't want to convert nothing. Divided by 1.3. This is the answer that we had calculated initially. So the answer, okay, 0.15 divided by 1.3 is this, and then to 2 decimal places is this, and then we say 1 multiplied by 10 to the power negative 40. I just want to make sure that I don't convert nothing, so divided by answer, and that is equal to what the let me say 7 and 3. Okay, this is the is this really true? Yeah, I think it is. Let me make sure. 0.12. Okay, so we have 8.3 something, but it's not actually that, so it must be. Please don't mind me. I had already determined the answer already, so please do not mind me at all. So we have 0.15 and then multiply by 0.1. Okay, so it is actually 67. So 8.67 times 10 to the power negative 14 moles or moles per cubic decimeters. Okay, so this is the concentration of the hydronium ions. It is 8.67 times 10 to the power negative 14 moles per cubic decimeters. Now that we have the concentration of the hydronium ions, we can determine the pH by saying pH is equal to negative log of the concentration of the hydronium ions. So we're going to be like negative log of what? Of 8.67 multiplied by 10 to the power negative 14. What is that equal to? That is equal to, no, it's not going to be positive. So we're going to be like negative log of answer, and we get what we get let me say 62. We get 13.06. So we have 13. How do I write 13 from this? Okay, let me just do this. Okay, 13. So 13.06. So that means pH is equal to 13.06. So what does the pH of 13.06 tell us? It tells us that the solution after completion, or after completion, or after titration, or after neutralization. Oh my god, it is so nice when you know all these terms. After neutralization is basic. Okay, so I'm so sorry that I can actually see that. Okay, that's better. Okay, so what this means, the pH of 13.06 means that the solution after completion or titration or neutralization is basic. Why is it basic? If we are just to ask ourselves, why is the solution basic after completion? It is basic because remember what I said. This is an acid neutralizing the base, but the base is in excess. That means the acid is going to react with the base and is going to react completely. However, the base is going to remain after completion. So that the fact that the base is going to be the one that remains after the completion or after titration or after neutralization, that means that the solution has to be basic because it is the base that is going to remain. It is the base that is in excess. So it makes sense for the solution to be basic because it is the base that is going to remain. So the pH of 13.06 makes absolutely, like, it makes sense. Let me just say that. Okay, so yeah, it does make sense. So 13.06 means that this is a very strong base. So that means sodium hydrogen carbonate is a very strong base. So this is a very, very strong base from the pH that we have just calculated because it is closer to 14. So that is how we answer this question, and that is how we get our 17 marks. Is that 17 marks? Let me just confirm quickly. yeah, it is 17 marks. So that is how we get our 17 marks. So that is how you get your full marks in a system basis question. So I hope that I've explained it in a way that you understand, and I hope that you have enjoyed the video. Please save the video in case you're going to need an explanation like this in the future. Okay, so we're going to meet that again in the next videos. So thank you very much for watching until this far.